Hi guys, it's Lindsay and Taylor. Sorry, say hi Taylor. Okay, today we're going to show you how to do arc length and surface area. Okay, finding this whiteboard and stuff has been challenging, but we're gonna do this. Okay, let's go to arc length first. Woo. Okay. Okay, so let's find this. Okay, so our arc length. Essentially, what arc length is finding the distance between any 2 points on a curve. We already know how to find the distance between 2 points, and like I already have written up here, the distance formula will kind of give us that. So if we have like this linear graph, we would use this distance formula to find, the distance along any 2 points because um, well, it's easy. Like if you just look at this formula, it's obvious that this is coming from the Pythagorean theorem because, we just use x and y to find this length right here. Okay, but with an arc length, this obviously cannot work because this is a curve, and so the distance formula cannot be really used in this instance. And just another way to kind of think about arc length was so if you have like a string and you lay it across this graph right here, kind of the length of the string between the 2 points that you have chosen or that you put down on here. So like from here to here, let's say you were to lay a string out on this, the length of that string would be the arc length of this curve. Okay. So even though we can't really use the distance formula itself because this is a curve, not a straight line, this distance formula does play an important role in kind of where the formula for arc length comes from. So if you remember back when we were first doing integration, we had the Riemann sums. I hope that's how you pronounce it. And essentially we're taught to take a bunch of those little shapes to kind of estimate, what the area underneath the curve would be. Well, for arc length, we can kind of think about it and approach it in a similar manner. So let's say we broke this up into a bunch of little sections. Sorry, I haven't perfected this art of using this whiteboard app yet. But let's say we had a bunch of little like lines, right? Because we have the distance formula, and so we could just kind of approximate the distance of this arc length by doing a bunch of, well, supposedly straight. I didn't really draw them straight, but a bunch of like little straight line segments, um, of which kind of have the, y and x. Um, yeah, they have the y and the x values, and that will essentially give us, this little length for just this little approximation, which we can kind of call S, I guess. Haha, that rhymed. Okay. Um, so essentially, like if you think back to when we were doing the Riemann sums, we learned that an integral was to just infinitely add like infinitely small numbers of these sums to get the exact area. Well, we would do a kind of similar thing in this instance, in which we would just add infinitely small of these little like distances, these little lengths that we would get using the distance formula. Just we would add infinitely small numbers of those to get the actual arc length. And so because of this infinite adding, we would use an integral, right? But instead of using the like an actual like equation and then dx because that would be what we would use for area, we are just finding this little line right here, this segment, and so we can call it this change in s. And if you remember, change is written as d of whatever variable. So we're using s right now. It's not x or y. It's just this change in this length because, like I said, we're just adding an infinite number of these little lengths, which is shown by the integral. And just a little note about notation: this triangle, which is delta right here, that means change, and so does ds. Um, So right now we have this as kind of what is representing what we want to find for our arc length, but we can't exactly work with this. We can't compute it. We know kind of what it means in theory, you know, um, but to find what, like to get it to a way in which you can compute it, we can kind of substitute the distance formula for ds, because ds, like I was saying, is representative of this change in this s value, which is what we want to find as it changes along here, in order to integrate it and get, um, the arc length. So we can also rewrite this as the arc length of, remember how I said the d is kind of the same as saying delta, or like the little triangle right here. So dx squared plus dy squared. So that's kind of the same thing, but still we can't exactly integrate this yet because it's not exactly in a form that we've seen. We still kind of are defining it by two terms, x and y. Can't really compute this yet. So what we can do at this point is we can kind of, well, we have to think of the, mean value theorem in order to kind of like get this down to a way where we can compute it. And what the mean value theorem essentially says is that if you connect 2 points on a graph, the slope of the line between the two x values exists as a value on the line of the derivative between those same two x values. So essentially what this means for us, I guess mathematically, well, it's all math, but yeah, I'm awkward, sorry, is that if we have the derivative of a function and we plug in a certain x value between those two bounds, it's going to be equal to this slope that we have of the two bounds. So essentially this is kind of what we can get from the mean value theorem. But then if we rearrange this, it becomes helpful to us in terms of arc length, because we will have the derivative of the at the certain x value times, I'm running out of space here a little bit. Uh-oh. Let's move over. Sorry, excuse me. So we'll have the derivative of the x value times dx, that will be equal to dy. So we can kind of replace that right here and write it as the integral of dx squared plus fx dx squared. Okay, right? But so this is still looking a bit awkward though, and we can kind of still continue to rearrange this stuff. Okay, so now we have, if you look, we'll have, you can see that we have dx squared in both of these terms, so we can, of course, pull that out. So after pulling that out, excuse me, we will have dx squared times 1 plus the derivative squared. Well, I wrote this really cute. Yikes, okay. Yikes, 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 yikes. Yeah, you know what I'm writing. Yeah, that's fine. Okay. Okay, and because these are being multiplied to each other, we can thus see that this square root is being applied to both this term and this term, and thus we can pull this out even further, and we can then rewrite it again as this bad boy. And bam, we have something that we can integrate. Of course, you have to have your, okay, well, that was fabulous, your upper and lower bounds. But essentially right here what we have is the arc length formula. Oh my god, I am just trying to highlight it. Okay, yeah, so this is the arc length formula. Essentially, you just have to plug in, your derivative of whatever function you're using, and then know your bounds, and then you can find the arc length of essentially any curve now. It does not matter. Well, at least I think it doesn't matter. But yes, here is your equation.
Okay, so surface area is essentially just the area, which is just base times height, but because we're finding the surface area of a revolving solid, we have to take an integral with bounds of base times height. And because we're revolving, we are using circles, so the base in this situation equals circumference. So surface area equals circumference times height. And circumference in this scenario is just, well, circumference always is just 2 pi r. And r can either equal y or x. Depends on whether you are revolving around the x-axis or the y-axis. So we know that base equals 2 pi r. Now we need to look at height. And so again, height is arc length. So height is the integral of a to b of the square root of 1 plus f prime of x squared dx. So we know what base is, we know what height is, all of the arc length. So we know that surface area, which is just base times height or circumference times height, equals 2 pi r times arc length, or the integral of a to b square root of 1 plus f prime of x squared dx. And it could also be rewritten as a 2 pi r times the square root of 1 plus f prime x squared dx. So you can take one integral of all of it, and that is your surface area equation.